whether to use the board or slides, and in the end there were three reasons. The first is you can remember my co-authors now. You can see them again, Hajia and Pravesh Kothari. The second is the font is better than what I can write now, even though I will go slow. But I think the third, maybe most important reason is the last half of the room cannot see half the board. Okay, so what is this? Let me quickly introduce the problem. It comes with a fancy name, independent component analysis from statistics. And so you are given samples, and I have to tell you how the samples are drawn. You start with independent random variables, D of them, and then there's an affine transformation applied to it. A joint affine transformation applied, and that's what you observe. So you observe X, which is an affine transformation of a product distribution. Okay, and the problem is to estimate the transformation from the sample. Okay. Estimating the shift is not hard, just take the average, but estimating the transformation is a little bit more involved. Turns out that, if you think about it, this is uniquely identifiable up to scalings of columns, because scaling a column or scaling the original random variable is the same thing. So up to scalings of columns, as long as basically the components are not Gaussian. If they are Gaussian, then it's rotationally invariant, and you can't tell the difference between two A's which are just rotations. Okay. But otherwise, you can, as long as. This is a problem. The model has been used extensively in applied areas. People came up with it independently, and so on. Is the problem definition okay? Yeah, to see your samples? Okay. I will show it to you from two more perspectives. This is a question from 2015 at a winter school in Paris. Talon asked me, can you efficiently distinguish a convex body close to an L1 ball from a body close to an L2 ball? Okay, this will be very closely related problem, okay? Okay, close to is not well defined, but he just meant close to in some generic sense. Okay, so here's another view in case. So here's the problem. You can think of it as learning a parallel pipe, right? So you start with, say, uniform distribution in a cube. So it's a product distribution. There's an affine transformation applied to it, and you just take a sample. Okay? See, I cannot do this on the board, but so there's an affine transformation, and you want to output this transformation. In what? What guarantee do you want to give for this? Yes?
But close to L1 ball will be square root of n to the power n smaller volume.
Okay.
The volume will be much smaller.
No, we'll scale it so that you cannot tell just by extreme points. And he's a clever guy. I mean, it's not. What is the guarantee? Of course, I can produce some affine transformation. What guarantee do I want? The guarantee that we want is that the resulting cube or parallel pipette that you produce should be close in total variation distance, so in L1 distance. Okay? If you view it as distributions, they should overlap in basically 1 minus epsilon. Okay? Okay. This is a crucial part of this. Okay. So this problem was solved and formally. I think the earliest one proof I know is by Fries, Jerem, and Cunningham. And what they said, first you can observe that just finding singular vectors doesn't work, because of course all rotations will give you no information. Okay. So nevertheless, let's first make it isotropic. Let's first make the observed distribution isotropic. So now you can assume that your unknown transformation A is a rotation matrix, is a orthonormal matrix. And then, this is the main trick, let's find directions U that are local minima of the fourth moment. So find fourth moment minimizing directions. Okay, forget about algorithmically how, just find fourth moment minimizing directions. And this they will do just by some gradient descent, some very local algorithm. In general, this is a hard problem, but for this setting, it'll turn out you can do it efficiently. Okay, so I want to convince you that this works. So they will say that after placing in isotropic position, the local minima of fourth moments are in fact the facet normals. So why is that? this is the formula, that's it. This is all you need to see. The expectation of in any direction u, we can write it as this difference between the fourth moment of the component distributions for the cube minus 3, a constant, times u transpose ai. Ai's are referring to the columns of A, plus 3. Now, if you believe this formula, which I will do the calculation here in case so that you believe me, then you'll notice that as long as the fourth moments are not equal to 3, those directions are the only possible minima or maximum. Because this is fourth power. If that had been second power, of course, anything with equal coefficients will work. But if it's fourth power, the extrema will have to be AI, no option. Okay. And so, as long as at least one component, at most one component is Gaussian, this works. Now, let me just show you. I suppose I could write on the screen, but right. Thank you. So what do I want to do? Go back to the statement. Oh yeah. I want to do that expect x, remember, is is A times S. I have done this before. And I take some direction u, and I'm looking at expectation of x transpose u to the fourth, right? So we expand this, and this will be a summation over the coordinates of s, or u, yeah, s is better, si times the ith column transpose u, okay, or I want this expectation. Okay, and now fourth power, so we will simply write it out as over all four coordinates, I, J, K, L, and you'll see you'll get 4 of these, fine. AI transpose U, AJ transpose U, AK transpose U, and A. So 4 columns, potentially 4 different columns. And then the only random variable is the product of them. And these are independent by assumption. So we've also made the distribution mean 0 and isotropic. So the only things that will show up here are when all 4 are equal or 2 pairs are equal. So I'm going to be left with the expectation, well, first of all, I'm going to take it inside, over I of Si to the 4 with AI transpose U to the 4, that's one set of terms. And the other one will be over I not equal to J, but there's going to be 3 of these, right, depending on which pairs, either I is J or I is K or I is L, of AI. So expectation of Si squared is 1 and Sj squared is 1, so all I'm left with is a constant term, which is AI transpose U. Right? And now we just let's add in the missing I equal to J terms here and subtract them from here. So we'll be left with, sorry, minus 3. I'm subtracting from here. And here I'll be left with 3 times just a double summation, which is A trans AU squared. A is orthonormal, so this is just the length of U squared. U is a unit vector. This just becomes 3. Okay. That was the formula. Sorry? I just mean this because we have Okay, so that's the formula, and you get going back to what I wrote there. That was their method. Okay, great.
So you have an unknown matrix, and you're allowed to evaluate it at any given vector?
No. You are given samples X, which are this unknown matrix applied to a product distribution.
Applied to what?
A product distribution.
So you have random samples?
Yeah. The model is the following. Let's just. There is an unknown product distribution S. Let's assume it's isotropic. And this is an affine transformation applied to it, and you see samples from it. So you see uniform samples from a parallelepiped. Uniform points from a parallelepiped, unknown parallelepiped. And you want to estimate the parallelepiped.
You want to find A.
You want to find the, yeah, sure.
But you have control of what distribution you...
It's a uniform distribution. Suppose I give you uniform samples from a hypercube, and you want to estimate the cube. Mm-hmm. What will you do? I'm giving you random samples from a unit cube, and you need to estimate the cube.
But it's a unit cube.
Yeah, I tell you it's a unit cube.
Rotate.
Yeah, it could be rotated, it could be shifted.
Okay.
It's not set, so you need to find the shift, which will be the mean, and then you need to find the rotation, which is non-trivial. You can solve it like this. Yeah. And the part about transforming parallelepiped to cube is no problem because you can apply an isotropic transformation. But great, thank you. Keep with that. Okay, so let's go back to Millman's problem. So he makes it isotropic and scales it so that it's intersected with a suitable multiple of B, of the unit ball, Euclidean ball. And then the other body is something close in Banach-Mazur distance to the unit Euclidean ball, and you want to tell them apart. Okay, and you have access to these bodies. You can test, are you in the body or not? Are you in the body or not? That's it. You basically have access to these bodies. So yeah, can you tell algorithmically? And the answer is yes. This is part of an email. You don't have to read all this, but basically you can generate random samples yourself because you have a membership oracle. This is something we know how to do efficiently. Okay, so whatever body is given to you, generate random samples. Then from those random samples, estimate this tensor that we used in the previous algorithm, and then you can find the local maxima of this tensor by simply doing something like a power iteration. Okay, this will converge very fast to local maxima. Great. And then you don't need to find all of them. Just find, like, say, 100 of them and check in that span. Okay? You know by Dvoretsky that in the second case it will look like a ball. And in the first case it will not look like a ball because these things are really pointed. And that's it. That's the test. Okay. So I wrote this to him and he replied, and it's a nice reply, so I wanted to show you here. I think the talk is not recorded, right? Anyway. It was presented in their seminar. It's a nice idea how you distinguish exactly. Okay. In the same time, this was a baby problem. What I really want. I know that I asked exactly this because I did not see also what you did. But the original question was to find the difference between, say, 2 isomorphic L1 and 2 isomorphic L2, okay, or tenor. Your method works with perturbation by very small measure volume, but not by perturbation in BM. That's absolutely right. Actually, in such a form, we wrote this question in the last section of my paper with Pluskin. It's a very nice paper from 2004. And, okay. So I've been busy since then, but there is some progress to report. Just to summarize what you can happen there, you can extend this. So of course, there are many distributions with fourth moment equal to that of the Gaussian. It turns out that by going to higher moments, you can solve the problem entirely. Because there will be some moment in which you are different from a Gaussian if you are not Gaussian, and you can extend this method to higher moments and actually solve the entire problem based on whatever is the moment number at which you differ. Okay, and it also works if you take your data and you add some unknown Gaussian noise to it, mild, benign Gaussian noise. But the problem I'm going to focus on here is what if the noise is arbitrary? What do I mean by that? I'll define this precisely. It sounds like yeah, okay. So here's the question. You're given samples again from a parallelepiped, okay, uniform samples from a parallelepiped, from the uniform distribution, except an epsilon fraction of them are arbitrarily corrupted. So there is some epsilon fraction of them that can be changed to whatever you want. by somebody who knows the distribution, knows the algorithm and so on, but they can only change epsilon fraction. So 1% of samples, they can do whatever they want. Okay? Can you still learn the parallel pattern? But now within total variation distance.
They're arbitrarily corrupted within the parallelepiped or
no, anywhere in space. Anywhere in space. So it's this adversarial corruption. Okay. Now, this is still information theoretically possible because they only changed epsilon fraction of the points. So you could, for example, guess every possible epsilon subset, right? And in the remaining for the remaining 1 minus epsilon, find a parallelepiped, and among all those, take, let's say, the minimum volume one. Okay? So this is possible, the TV distance guarantee. The question is, can it be done efficiently? So you see, the flavor is you're taking an arbitrary perturbation of the parallelepiped and you still want to recover. So this is, of course, the best possible guarantee because you can't do better than epsilon TV distance since epsilon is being changed. So that's the question. And here's the outline of the talk. I'll briefly motivate this topic of algorithmic robust statistics. Mention an interesting challenge we'll come across for this problem, and then show you an algorithm that still works. And some questions that maybe you're interested in. Okay, so robust statistics is an old field. And the idea is exactly this. You know, you have samples, and you want to fit a Gaussian to it. Great. But what if the data is actually coming from a Gaussian with a fraction of the samples completely arbitrarily corrupted? Can you still estimate the underlying Gaussian? It's a non-trivial problem. And yeah, so for example, if you want to just estimate the mean, you can't just take the sample mean. But we know in one dimension you could use the median, and that in fact is an optimal robust set. So that's the general setting. But you can do this to whatever model your distribution is being drawn from. So, you know, you could ask to estimate the mean or the covariance or a mixture of Gaussians, a classical statistical model, or you're seeing observations from a Markov model and you want to estimate that, so on. Now, there were, of course, classical approaches proposed by Huber and Tukey and other statisticians, and they turn out to be beautiful ideas. For example, one of them is called the Tukey median, which says, take the smallest volume ellipsoid that contains 1 minus epsilon of your points, and take its center. Output that to be your mean estimate. Turns out this has a very good guarantee. But finding the smallest volume ellipsoid that contains half your points is a computationally intractable problem. Okay, you could do, how about median? You know, you could do median in each coordinate, or something called the geometric median. The trouble with these is that the error of the estimate grows with the dimension. Whereas in principle, there should be no dependence on the dimension. It should just be, because that's the information theory. So in 2016, there were 2 papers which solved this problem for the basic question about estimating the mean and covariance of a Gaussian with arbitrary noise. And then more recently, in 2022, there is a paper which solves this for a mixture of k arbitrary Gaussians, completely arbitrary Gaussians. They can have 0 covariance in some direction, their mixing weights could be arbitrary and so on, and still you will be able to estimate the mixture of these Gaussians despite epsilon fraction of arbitrary corruptions. Just a quick summary. Now, the basic philosophy in these results is that to do robust estimation, there are now many problems that have been solved using these ideas, is that if you can robustly estimate low degree moments, which of course is exactly the first problem we posed, mean and covariance, but even for something like a mixture of Gaussians, if you can estimate low degree moments robustly, then there is enough information there to recover the actual parameters of the distribution. For example, of course 2 moments fix a Gaussian, but 6 moments fix a mixture of 2 Gaussians. And this is already from Pearson. But making this algorithmic took a century. And indeed, constant degree moments of a pretty general class of distribution can be robustly estimated in polynomial time. This is a result that follows this slide. So in polynomial time, using a convex program, you can actually estimate any constant degree moment. Great. Now, I don't want to say that going from moments to the actual parameters of the underlying distribution, like mixtures of Gaussian, is not trivial. It takes a lot of work, depending on the problem. But nevertheless, information theoretically, the moments suffice. And then there is a challenge of turning them into it. Okay, and it's an interesting, relatively new area, the algorithmic processes. Okay, now let's go back to this problem. Can I learn a parallel pipette to within TV distance epsilon when I have arbitrary corruptions? Right? So there is a solution. Find the smallest volume parallel pipette that contains about 1 minus epsilon of the samples. Okay. But how? How do I find the smallest volume? Right? Or even, yeah. Let's take a simpler case, which is the only thing I do is I shift. So it's oriented cube. Okay, I started with the standard set cube and I shifted it to an unknown place. But now epsilon fraction of points are arbitrarily corrupted. And all you need to estimate is what was the shift, a single vector. Okay? Can you do this? How can you do this? Right? Well, it sounds like this should be what is done already, right? Estimate that mean robustly. Okay? Like I said, we can do it for a Gaussian. Estimate the mean robustly. You can do it for hypercontractive distributions. This doesn't work. The problem is this. Maybe therefore this the board would have been better. Imagine I shift by epsilon in this direction, diagonally. Then I'm shifting by epsilon over square root dimension in every coordinate. And the total variation distance is actually about epsilon times square root d. Right? Two cubes which are diagonally shifted by epsilon have very little overlap. So even though you might have estimated the mean correctly in L2 distance, which is the best thing you can do, it's not enough to get a total variation distance estimate. Okay. So even if you can do the mean estimation optimally, robustly, which we know how to do now for hypercontractive distributions, it's still not going to solve this problem. Because there is this unknown, I mean, there is this basis in there, sitting there. And the same thing for a rotation. If I estimate each facet to within epsilon, this can have a huge error in the total variation distance. Okay. So moments do not suffice, and this is a theorem. So if you only have optimal estimates of the moments all the way up to log d over log d, so more than constant number of moments, it's not going to be enough to solve this problem, even for mean estimation and also for rotation. Okay, so we really have to do something new beyond moments, as far as I know. So it seems like an interesting problem, right? So, and this is what I mean by certificate. How do you certify? What would be the? I mean, at the end of an algorithm produces a certificate, and because it's short, just the execution of it. So, what is the certificate that the mean you're claiming as the mean is actually close to the true mean? Okay. So, some observations. Let's also introduce diagonal scaling. So it's still in the same unit. I'm not rotating at all, but I'm scaling the diagonals. Okay, so the matrix A is just diagonal and a shift. In this case, you know, the total variation distance is just going to be linear in the mean divided by the standard deviation. And let's assume that for a second, the simplest problem again, there's no scaling. Now there's an observation. That if I could estimate the mean in L1 norm, then I'd be done. Not L2 norm, but L1 norm, if I can estimate the mean, then I'll be done. Because then the total variation distance is going to be bounded by the L1, right? Because it's proportional to the mu i's. TV distance in each coordinate is just the mean shift up to constant, and so the total TV distance is sum of these mean shifts. So if you can estimate L1 norm, but that's impossible to do in general. So let's see how to do this. So I'm just doing the baby problem, which is I have a cube, samples from a cube that's shifted, and I want to estimate the cube, but the shift, but the epsilon fraction are arbitrarily corrupted. Okay. how should we do this? So I'll show you a little algorithm which is not published anywhere, but it's kind of like a magic trick, so it's fun. It won't work for the general case with rotations. For that, I have to give you this more elaborate algorithm that needs a proof. We wrote a paper and all that. But here is a nice algorithm. So remember, we have some underlying cube we don't know, and I have samples from that. 1 minus epsilon, certainly from that. And then epsilon, I don't know where they're from. They could be off the board. Okay? This is this cube, I don't know, but I'm trying to estimate its mean. So here's what we'll do. I'm going to define a graph. So this will be a combinatorial proof, okay? In honor of the chair. But, okay. So here's the. So I'll define a graph. The vertices will be just one per point, one vertex per sample. Great. What are the edges? I'll put an edge between I and j if the corresponding points, say xi and xj, wherever they are, there exists some coordinate, say k, such that, so in other words, if the L infinity norm between xi and xj is bigger than 1. So if they're bigger than 1 in some coordinate, I'll put an edge between them. So in the points that came from the original cube, there's no edge between them, because they're all within L1 L infinity distance 1. But something from here to here, there could be an edge. There could be an edge from here to here, and so on. Okay, so you have a graph. Edge means you're farther than 1 in L infinity distance. Great. What do I want to find in this graph? I claim this graph has an independent set of size 1 minus epsilon, or fraction 1 minus epsilon. There exists an independent set of size at least 1 minus epsilon. Why is that? Because you only corrupted epsilon fraction of the points. So 1 minus epsilon are from the original cube. They form an independent set. Now, what is the complement of the independent set? Some set of vertices which form what's called a vertex cover. Right? A vertex cover. Meaning that all edges of the graph are incident to them. Okay? So if I could find this vertex cover, the rest of the graph is independent set. Of course, finding a vertex cover can be hard. But we have approximation algorithms for it.
Why are there vertex cover? You're assuming that the other points are outside the cube.
Well, the complement of an independent set is a vertex cover. All I'm saying is there exists a vertex cover of size, yeah. So there exists a vertex cover of size smaller than epsilon. That's all. And we know how to find, if there exists a vertex cover of size k, we know how to find one of size 2k by simply computing a maximal matching and taking both endpoints. So let's find a vertex cover of size 2 epsilon. Great. Its complement is still an independent set of size 1 minus 2 epsilon. We're done. We've got 1 minus 2 epsilon pure points, and now estimating the cube is easy. Just take the max and min in every coordinate. That's your cube. And its center.
So I still don't understand. You're assuming that the bad points are outside the cube.
No.
So why? So you found an independent set. So it could be the corrupted points are still
Yes.
are among those.
Absolutely. Absolutely. The point is
why cannot change the center of the cube?
Because I'm not using their mean to estimate. I'm just using the min and max coordinates. So what's the final estimate? I get 1 minus epsilon points, which are all from the original cube, potentially.
But including ones which could be unrelated to the distribution, to the uniform.
Absolutely. And then I take the max and min in each coordinate.
Mm-hmm.
That will be some cube, or cuboid if you like. They could be slightly off in every direction. And I take its center. And I claim this center, right, is going to be close to the original center.
So you have to prove something regardless of the corruption.
Yeah. But this is a, yeah.
Because it could be just some deterministic.
Right. But you see, the point is that if I have a cube within a cube which contains 1 minus epsilon of the points, it's basically almost the entire cube, and its main has to be close.
This is to prove something then.
Right. I mean, the proof is just saying that the total variation distance is at most the L1 norm between the mean shifts. And it's actually lower bounded also by that. Okay, that's it. Okay, so this is the combinatorial proof. What it means here. Unfortunately, this kind of style of proof doesn't extend to more general settings. But even if I have a shift, I don't know how to do it. So let's do that first. So now we're in the setting where I have a cube It's been stretched arbitrarily in different coordinates and shifted. Okay? Stretched and shifted. So diagonally scaled and shifted, and you want to estimate the diagonal scaling and the shift. That's it, right? The previous algorithm no longer works because I scaled arbitrarily. So I cannot say if infinity is greater than 1. I mean, each coordinate has its own width. Okay. So here's what we'll do. This is the certificate. This is the certificate. It's going to be a test that uses only one-dimensional and two-dimensional projections. That's all. So first, we'll start with the coarse approximation. That's actually easy to get. We'll start with an interval, which is, you start with an interval that contains, say, half plus epsilon of the mass, and double that. So it will contain 1 minus epsilon of the mass in every overall. Okay? That's your starting cube. So this definitely contains the original cube. That's easy to get. We'll just do that separately in each coordinate. Okay. Now, here's the thing. We know that the true cube is uniform, of course, which means that if I look at an interval of some width, say W, the fraction of points should be W from the true points. So what I'm going to check going from the outside in is that intervals of width epsilon over d, 2 epsilon over d, 3 epsilon over d, multiples of epsilon over d are dense enough, right? We want to make sure that they contain at least, so they are supposed to contain epsilon over d, the width fraction of points. If they contain very few, I'll move in the boundaries. Like few means how much? Smaller by a constant fraction. So if it's less than half what it should be, we'll move in the boundary. If it's at least half of what it should be, don't move in. And we do this separately for each coordinate as long as some coordinate can move. And this might happen back and forth. But you check at the stopping point, you know that for every coordinate you can move in, you cannot move in because the outermost epsilon over d, 2 epsilon over d, 3 epsilon, they all have what they should have divided by 2 at least. So their density is at least what it should be, half of what it should be. That's all you've checked. Okay, so that's one dimension. The second thing we'll check, and this is how you could be thrown off, is that the intersection of any such pair of bands, well, that should have about, a width squared points, width squared fraction of points. We want to make sure it doesn't, not too many. If it's more than, say, 10 times the product of the widths, we will throw out all those points. See, from the true uniform distribution, the maximum, what you could have had there is exactly the product of the widths, because the product distribution. But if you get 10 times that, that means the adversary put them there. So we'll throw out all. But we don't know which ones they put, which ones they didn't put. We'll just throw out all. Okay? So if it's more than 10 times what it should be in the intersection of pairs of bands, we'll throw it out. That's it. That's the whole algorithm. Keep doing this. Obviously, you're making progress. Till you can't do any more, stop there. Estimate, output that cube as your answer. That not cube, but it'll be a box. Okay, so the theorem is that the volume of the symmetric difference, you will produce hat h, and the true cube is h, is at most 4 epsilon times the original volume. And here's the proof idea. Suppose for a second that the outliers affect only one coordinate each. This is a completely unrealistic assumption. I mean, outliers meaning the noise, either a point that was moved or a point that was added, right, affect only one coordinate. Somehow they only affect one coordinate. Then you see the total number of bad points is epsilon n. That's the budget the adversary has. Every time you don't get the right density, that means what? The adversary has spent proportional fraction of their budget in removing points, and every time you throw out points from an intersection, the adversary has spent proportional amount of budget there. Right? So the total number you can keep doing this is points you can throw out is at most epsilon. Can't waste more than that. But the problem is, of course, that this assumption is completely artificial. Of course, an outlier can affect all the coordinates potentially. It could make the density look different in n coordinates by moving it along the diagonal, for example. So for this, there is a combinatorial lemma, which I have tried to find a reference for, but I haven't found a reference. But there are enough or should I say, experts in this room that maybe you will tell me a reference. So here's a lemma. I have subsets of 1 through n. And let me denote by f of s the fraction of n, the fractional size of each subset. And suppose I tell you that the union takes up only an epsilon fraction, and that the intersection is at most alpha times the product of the fractions. Alpha is some number between 0 and 1. Okay. Alpha is just a number. But then I claim that the sum of these fractions is at most is only a little bit more than epsilon. Okay. So you have a universe of you have a set of subsets of 1 through n. Each of them could be whatever fraction. Together, the union is only an epsilon fraction, and they have this pairwise intersection. The intersections are bounded pairwise. And you want to say that the sum of their sizes is small. Okay. This will immediately allow us to say that the previous analysis is formally correct, because even if I account for outliers separately for each coordinate, I can only overcount by 1 over 1 minus alpha epsilon. Alpha was chosen to be a constant like 10. So underlying this, so this is what I just said, is you can turn this into a purely probabilistic statement. I should have some high-dimensional probability. So if you have Bernoulli variables they're not independent, with the property that the expectation of the product xi xj is at most epsilon times the product of the expectations, then indeed the sum of the expectations is at most 1 over 1 minus epsilon. This is not inclusion-exclusion. I spent several days trying to so I don't try inclusion-exclusion. But I will show you the proof in the last proof break. It will take the same amount of board space. Okay, but let me continue. We'll postpone the proof break to the end. Yeah, there is some danger that people might just not pay attention to the rest of the talk. Fine. Okay, but we are left with rotation. So far, we've only done shift and scaling. What about rotation? This turns out to be the most involved part of it, estimating rotation. Let me focus exclusively on it. Suppose all you've done is taken a cube and rotated it. No shift, no scaling. Okay. How do you estimate this? So we can start with coarse estimates of the normals, which come from robust mean estimates. You can start with an estimate so that if your original rotation matrix is the AI star, you have estimates AI hat so that their L2 norm is at most, say, square root epsilon. This you can do in polynomial time. Okay. As we already argued, this doesn't give us total variation distance because these rotations could together make the distance super long, super high. So now what? So here is the kind of key lemma, that for any orthonormal A and any other A hat with unit length rows, the total variation distance between A edge, so some rotated cube, and this A hat edge is bounded within constant factors of the sum of distances, not square, but sum of distances. Okay? The sum of L2 distances. This is not hard to prove, but this is an important lemma here. And you can see that this will give you epsilon, something increasing in dimension. So we need to bound this, we need to find an estimate of the matrix where this sum is actually quite small, this norm. And even if you manage to do it in Frobenius norm, it won't be enough. Because Frobenius norm will just improve from D to root D. Right? If I find a hat, so that A minus A hat is within epsilon in Frobenius norm, even that's not good enough because you'll get epsilon root D in the sum of distance. Okay, so how do we estimate the rotation? Here's a new algorithm here. So let's first do it for the no outlier case, which we know how to do, but this is a different algorithm. And that's one of the nice things that happens with these robust statistics, that even for problems with no noise, there seem to be new algorithms coming out, like with this. Anyway, so what we're going to do is we'll start with these coarse estimates and do a local improvement. Okay, how? Let's consider, there's a figure coming up. Sorry, here it is. Consider that for for a direction A, let's consider the half space, which is just everything at distance bigger than 1 on one side. And similarly, we have minus A, with a bit less than minus 1. So points that are half space on that side and half space on this side. And what we'll look at is for your current A, let's look at the points, the samples that are outside this in this direction, and the negation of the opposite side. So let's just focus on one side. Samples that are outside there. And the claim is that the mean of those samples tells you which way to move. Okay. So you see, this cuts off some little cap of the cube, which is a pretty complicated object in general, but its mean basically tells you go opposite mean. Okay, and that's exactly the algorithm. You're going to update it by moving it opposite the mean, some multiple of the mean, and renormalize to be a unit vector. Okay, and the claim is that this actually converges to the correct A. Okay. What we want to do is minimize the volume of this cap. Now, that's again we don't know how to do that. So instead, we're saying use the mean to tell you which way to move. Can we implement this with noise? So this works fine without noise.
Sorry, is it clear that the mean is non-zero without outliers?
Yes, remember my original distribution is a cube. So unless A hat equals A, the mean is non-zero. Yeah. But of course, the trouble is this was the algorithm I just stated so far. And the beta needs to be small, but not that small. It's inverse polynomially large. So it converges in polynomial time. But the mean itself can be corrupted by noise, of course, right? I mean, the mean of this is a tiny fraction of points potentially. The outlier, the adversary can do whatever they want with those points and mess you up completely. So here we will use robust mean estimation. Okay? And L2 error is just fine. So basically, here's what it looks like. We start with a coarse estimate. We define these half spaces. Okay? We're going to check the pairwise intersections of these bands. If any time the pairwise intersection is too high, we delete it because we know pairwise intersection cannot be more than the product of what it should be. Okay? And then we repeat this, where we robustly, so the number of iterations of this algorithm is only d log d, we robustly estimate the mean of what's outside, okay? And use that to shift the current point. And whatever points we deleted in this point, we're going to put them back in the next iteration and do it again, and do it again. And the point is this will monotonically converge to the correct. And give you the guarantee that the final set of vectors you get are in fact have small total variations. So I don't want to say too much, but the proof here uses the geometry of the cube very specifically. And the hope is that this can be somehow relaxed and made more general. But at the moment, we use properties like this just to give you a flavor. If your A hat, let's say EI is the true coordinate, and you are at some AI hat, which is at distance delta, then the volume of the cap can be bounded pretty tightly. The expectation, so the mean can be upper bounded, the variance can be upper bounded, and so on. And these allow us to give a choice of beta, which makes sure that when you make one step, you actually get closer. The distance gets closer by a small factor. And then how do we, so this is rotations. We did shift and scaling. How do we do it together? Well, we'll just alternate. So we'll run the shift and scaling algorithm, then run the rotation, then run rotation scaling, as long as one of them can keep going, and guarantee that in every 2 steps you will make progress or you will stop. And this is the final theorem. Given an epsilon corrupted sample of an unknown parallel pipette, right? Unknown parallel pipette. There is a randomized polynomial time algorithm that will find the parallel pipette so that the TD distance is order epsilon. Just a few remarks. The algorithm is quite different from finding 4th moment maxima, which actually doesn't work because those can be arbitrarily corrupted. There is this new parametrization in terms of this sum of L2 distances, and I don't fully understand what is the right way to think about, generalize it. Helgia worked on this for 2 years or more, which is unusual in computer science, but that's what it is. I will go back to the proof in a second, but maybe let me finish with the open problems. I still have 5 minutes, good. Well, actually, I should do the proof first, right? And then so what was it? Let's do the probabilistic statement. The xi are 0, 1 random variables, and I tell you that the expectation of xi times xj is at most epsilon times the expectation of xi times the expectation of xj. This is your guarantee for every pair ij, and you want to ask about the expectation of the sum of xi. Okay. And the claim is that this is at most 1 over 1 minus epsilon. Okay. This will imply, really? Why is this? Okay, so let's look at the square. The whole thing squared, and I would say this is at most the square inside. So far, so good. And now let's expand it. And then the second term is the over I not equal to j, expectation of xi times expectation of xj. Sorry, it's xi xj. Good. Now we will use the guarantee, which is this I can replace by expectation of summation of xi because it's Bernoulli, and then this one, and then that one is at most epsilon times summation of expectation of xi times expectation of xj. Good. Now let us overestimate this and write this as plus epsilon times expectation of summation of xi to quantity squared. Move the epsilon over to the other side, and I get that expectation of summation of xi squared is less than this, so 1 minus epsilon squared less than expectation of xi. Cancel one copy, and we're done. Okay. What is the name of this lemma? I don't know. But, so that's the proof. Open problem. Yeah, can we do this for more general product distributions? I only did it for uniform distribution. The fourth moment method works for anything whose fourth moments are different from Gaussian, for example. Right? And the general ICA problem without noise works as long as you're not Gaussian. Here, I don't know how to do it beyond parallelepiped. I really used cubic properties so far. Robustly estimate a simplex of an L1 ball. It appears that we may be close to this, but at the moment it's still an open problem to do this. LP balls, maybe. There is a lot of very nice structure we know about LP balls. Can that be used to robustly estimate from samples with corruption? And maybe this is one of my favorite open problems. I give you random points from an unknown bounded polyhedron. Right? So say at most m facets. And many quantities define this polyhedron. You get random points, and you want to estimate this polyhedron in PV distance. Okay. We know information theoretically we don't need many points. We only need about m times dimension over epsilon. This is to estimate this correctly. The question is, can you do this in polynomial? We just solved this problem for the case of parallelepipeds, but robustly. Now I'm asking, even without noise, can you do this?